Hi, my name is Coach Cowland, and we're going to look at frames of reference in this presentation. So when measuring motion, it's important to have a frame of reference. That frame of reference provides us with a baseline measurement, a start point, and it helps us to understand the context of the measurement. One of the reasons why we need to understand the context of a measurement is because the universe is full of motion. The Earth is rotating, it's spinning around the Sun, and the Sun is moving around the Milky Way galaxy. So not only that, there are various other types of motion that are going on. Usually when we're doing an experiment on Earth and we're measuring things on Earth, we use the Earth as our frame of reference. And we just assume that the Earth is completely stationary and everything else is ignored. Sometimes when we get complex scenarios like this, it's important to define our frame of reference so that we understand the measurements that we're receiving. So imagine that you're sitting in the green car and look at the other cars relative to you and the people. So the first person, person A, is sitting next to you in the green car. If you measure the speed that they were going relative to you, you'd say that they're not going anywhere. They are completely stationary. Now, why is that? Well, simply put, they're not moving away from you, or they're not moving towards you. They're sitting exactly stationary. So relative to you, their speed is 0. Now if you go to the next person, person B, who's sitting in the blue car, and they're going slightly faster than you, then if you think back to when you're driving in a car, you notice that when a car overtakes you, it looks like they're going very slowly, even though they might be going at, say, 70, 75 miles an hour, right? They only seem to be incrementally faster, very small amount faster. So their speed relative to your speed might only be 4 or 5 miles an hour, because that's the difference in speed between the speed that they're going and the speed that you're going. Now for person C, who's the person standing at the side of the road here, they will see you going past at quite the speed, and you'll be going past them at a very fast speed as well. So if you are doing what your odometer reads as 65 miles an hour, that's your speed relative to the Earth, and that's the speed that they're going to be traveling towards you, and you're going to be traveling towards them. Finally, in the yellow car, person D who's also traveling at 65 miles an hour, but in the opposite direction. Relative to you, that person is traveling at 130 miles an hour. Because you're traveling at 65, they're traveling at 65 towards you. So the combined speeds there, when you add them together, add up to 130 miles an hour. Relatively speaking, they are traveling very fast, even though they're traveling exactly the same speed as you. So if you were taking measurements here, it would be very important to define the frame of reference in which you were taking the measurements. And it would probably be best to take those measurements from the frame of reference of the Earth, which is where person C is. Now you could ask the question, which is the correct frame of reference? Which one of those is not just most useful, but actually the right one? Because I gave you a whole load of different values there. Surely there can be only one answer. So which one is it? The simple truth is, they are all correct. As long as you define the frame of reference in which you are in, there's nothing incorrect about the fact that the blue car is moving away from you at about 5 miles an hour, or that the yellow car was moving towards you at 130 miles an hour. These are all relevant frames of reference, but they need to be defined in our measurements. Okay, thanks for watching, and in the next presentation we'll look at speed and velocity.